Good morning, ladies and gentlemen. So, first I wish to express the deepest gratitude to our speaker, Doug Osheroff, who has agreed to participate in this initiative, and all of you, in particular our authorities, to come here to see Professor Osheroff. So, before giving a word to our speaker, I would just like to mention a few things. So this lecture is actually the first one on a series of talks which we are going to organize during the whole year. And the talks are made with the collaboration of the Fundación BBVA, and all of you know that they are eager to support science. And the colloquium is dedicated actually to the memory of the founder of the physics department in our university, which is, as all of you know, Don Nicolás Cabrera Sánchez. So this colloquium is dedicated to him, to remember his person to our young students and to try to contribute to the creative atmosphere of condensed matter, material science and applied physics departments. So one of the areas which Professor Cabrera liked is low temperature physics. So I think it's a good starting point. It couldn't be actually better to start with Professor Doug Osheroff. So Professor Osheroff, as you are probably going to see in his lecture, is an outstanding low temperature experimentalist. He built himself the machine which gave him his Nobel Prize, and actually he was a very hard worker, and his discovery was made pretty late at night, right? So around 2 or 3 or so, I believe. So he did his discovery during his PhD. And superfluid helium-3 has changed the way we look at condensed matter physics. So it's actually the purest material which you can imagine. And it's actually a material which shows up to the foreground, to the macroscopic level, complex quantum physics. And this is something which was totally new, and it was really a conceptual breakthrough. Of course, Doug is passionate about what he does. He's a passionate photographer, and he enjoys the laboratory and technical aspects of the laboratory. And apart his important recognitions in science, of course, the Nobel Prize, I would like to mention that he is a recognized teacher in his university, and I hope that you all will hear attentively to his lecture, and that you ask him many questions, especially the young among you. So thank you very much, and now it's your turn, Doug, and everybody has come to hear you. So thank you very much for coming, Doug.
Well, I'm very honored to be here today and talk to such a full house. I hope that those people in the back don't give up. It must be a very uncomfortable standing there for a whole hour. So I'll try to talk a little bit faster. Maybe then no. Anyway, this talk actually really starts from the beginning of what was the helium, the field of helium-3 physics. I should say that a lot of these images are mine, and this is one, and I'm afraid that your LCD projector just does not do my images justice, but that's true for everyone's. So we want to start, I suppose, to begin my life with the beginning of my life. I must record that, of course, in 1908, helium was first liquefied by Camerlionis. And it was quite remarkable because Onus was in competition with Dewar. Dewar had liquefied, I think it was hydrogen, and then he pumped on the vapor above the liquid, causing it to cool and ultimately solidify. So Camerlionis tried to do the same thing with liquid helium-4, and he pumped and he pumped, and of course helium, under its own vapor pressure, does not solidify at any temperature, including absolute zero. So Camerlionis basically gave up. But Camerlionis had an associate in the laboratory named Gilles Holst, and he started thinking about what other big questions of the day he could answer with this remarkable set of refrigeration devices that he developed. And so he procured a very pure sample of mercury and asked Gilles Holst to measure its electrical resistance as a function of temperature. And I think I'll show that later, but the bottom line is, of course, that Camerlionus in the process discovered superconductivity, although at that time I think no one understood what superconductivity was all about, and Camerlionus got the Nobel Prize very soon afterward, but it wasn't specifically for having discovered superconductivity. I dare say that what I have studied is helium virtually all my life, but I have two grants. One is a helium grant and one is everything else grant. So superfluidity in helium-4, of course, people began to realize had quite remarkable properties. And so in the 1930s, Kapitsa, Allen, and Meissner studied helium-4 extensively. It's kind of interesting. Ultimately, a Nobel Prize was given to Kapitsa, but in fact, Allen and Meissner did not share that Nobel Prize with Kapitsa. I really don't understand what the rationale was by the board that made that decision. Anyway, over the decades, people began to realize why helium-4 was so special. Of course, you could work out what the de Broglie wavelength was for helium at these low temperatures, and it became fairly clear after a while that one wouldn't have expected helium to solidify under its own vapor pressure. And of course this is, but what it does do, of course, it becomes a superfluid state, and this is really rather related to, but rather, I would say, quite different from Bose-Einstein condensation. Now, in 1948, Ed Hamel. Now, 1948, I don't know if, well, there are a lot of young people here who probably don't remember those Cold War years, but that was when the United States and the Soviet Union were competing, I suppose, in some sense, to build the hydrogen bomb. And there was a guy named Ed Hamel at Los Alamos National Laboratory who was responsible for keeping the United States' tritium supply clean, and what that entailed was, why was it dirty in the first place? Because tritium decays with a half-life of 12.4 years into helium-3, and so as time went on, you get more and more helium-3 in the tritium. Ed Hamel figured out a way to separate out the helium-3, and then he didn't throw it away or release it to the atmosphere. He actually saved it up. And without getting permission to do this, he decided he would liquefy his helium-3. And not only did he liquefy it, then he measured the vapor pressure as a function of temperature above helium-3. And then he published that. He actually published how much helium-3 he'd had. Now, of course, by doing so, he was telling the Soviet Union how much tritium the U.S. had and how long they'd had it. I actually interviewed him. I think he was quite old, something like 100 years old when I interviewed him, but he still had a very sharp wit about him. So helium-3, which really was prohibitively scarce back in those times, became available for study thanks to the nuclear arms race and the fact that tritium decays. It was found that the temperature nearly a decade below where one would have expected Fermi, the Fermi temperature for helium-3, the liquid began to exhibit behavior associated with Fermi degeneracy. So this is, in fact, a longer history of that. I mean, for me, it's very important, and so you have to put up with it for a while. Again, I'd said that Ed Hamel started out at Los Alamos, and he liquefied helium-3. That was actually a paper which Isaac Pomeranchuk, who was a member of the Landau School, read, and Pomeranchuk then, in fact, proposed a refrigeration process which I used in my discovery of superfluidity in helium-3. I'll talk about that later. In the 1950s, physicists studied the normal phase of liquid helium-3. They found that it exhibited Fermi degeneracy and had everything that one expected of Fermi particles, helium-3. Atoms are Fermi particles. Of course, in 57, Bardeen, Cooper, and Schreier, sorry, this thing is rather bright, and Schrieffer explained the origins of superconductivity, and very quickly theorists began to predict that liquid helium-3 might become a BCS superfluid. And the original, I think theorists do this on purpose, the original expected transition temperature was 80 milledegrees, which in fact was roughly a factor of 40 higher than the actual transition temperature. So theorists had made the prediction, and then really in order to get to those low temperatures, people had to develop new technologies. David Edwards at Ohio State University was the first one to observe a finite solubility of helium-3 in superfluid helium-4. Helium-4 becomes a superfluid at 2.1 Kelvin. And then John Wheatley had cooled helium-3 ultimately down to a temperature of 2 milledegrees, but did not find any evidence for superfluidity. He was working at saturated vapor pressure. If he had been working at the melting pressure, as I was, I suspect he would be up here giving this talk today rather than me. Anyway, Henry Hall then, in fact, invented the helium-3, helium-4 dilution refrigerator, which I think, I believe there are a number of helium-3, helium-4 dilution refrigerators here in this university. It's certainly a technology that's been really incredibly important for doing work at low temperatures. So very quickly, a worldwide search for superfluidity in helium-3 was underway. The original estimates for TC, as I said, were extremely, I would say, were optimistic, and while they were overly optimistic, in fact, they drove the development of new cooling technologies to reach even lower temperatures and to study Fermi degeneracy in liquid helium-3 itself. By the time I was a graduate student at Cornell University, I should tell you, well, I'll tell you that in a minute anyway. I came to Cornell. John Wheatley's group had cooled liquid helium-3 under its own vapor pressure down to a temperature of 0.02 of a degree, as I said, without seeing a hint of superfluidity. And I would say that the hope for a new BCS condensate had all but disappeared by that time. And so this is a picture of my family. My father was a medical doctor. My mother had been a nurse but gave up nursing to raise a brood of 5, I would say, unruly children. This is my older brother. My father was a medical doctor, and my older brother went into medicine as well. I'm son number 2 here, and I think I was probably about 8 years old when I connected the solenoid to a solenoid actuated relay to a battery. And when I removed the leads, of course, I got shocked. And so I packaged this up in a gym bag and brought it to school so that only a lamp cord stuck out. And if you squeeze the 2 prongs that normally go into the wall together, when you released them, you got a good shock. And so the kids were lined up, I would say, 20 deep to get shocked by my machine. I dare say I think I'm lucky that I wasn't kicked out of school. Anyway. So this was, I grew up in Aberdeen, Washington. It's a logging town in the Pacific Northwest. How many of you have heard of Kurt Cobain? Okay, several, all right. Well, Don Cobain was Kurt Cobain's father, and he, in fact, was in my class, graduating class at Weatherwax High School. So this doesn't show Don Cobain at all, but in fact this is the science club at Weatherwax High School. And I just wanted to point out, in fact, it was this person, my chemistry teacher, not my physics teacher, that profoundly influenced the way I thought about research. He came in one day with a milk carton, and he shook it. There was something inside the milk carton. He said, research is like trying to find out what's inside the milk carton. you can do an experiment. And every time you do an experiment, you're asking a question of nature. Nature has to answer your questions, but nature's answers aren't things like what's inside the milk carton, but rather something about what's inside the milk carton. So then you have to do more experiments in order to constrain your interpretation of nature's previous answers. And so, I mean, I sort of, after hearing that, I said, okay, so research is really a matter of tricking nature into giving up one of her secrets. And that's the way I always thought about research, and it's a wonderful way to think about it. So anyway, that's thanks to William Hawke there. This nerdy-looking character, that's me. Okay, that's enough laughter. Okay, I went to Caltech as an undergraduate, and that was when Richard Feynman was teaching the undergraduates, the freshmen and sophomores. It was a 2-year course on Feynman physics. So my freshman class coming in were 192 students. Only 120 returned for their sophomore year. And I think that Richard Feynman was probably responsible for the drop. But at the same time, I think that something fully 2/3 of the students that returned for their sophomore year wanted to declare physics as a major, and it was impossible to have that many physicists. I don't know why I got to be a physics major, but I did. And I dare say I think Feynman had a profound influence on certainly the ones that left, but also on the ones that stayed. So why did I go into low temperature physics? Well, the first semester I went to Cornell for graduate study, and the first semester there were 2 talks. One was a physics colloquium on the helium-3, helium-4 dilution refrigerator, and the other was a talk on Pomerantchuk cooling. And when I heard about these things described, I said, I want one of those things, and I wanted both of them, actually. And so I was actually working as a teaching assistant for David Lee, who was the head of the low temperature group. And so David Lee was very happy that I was decided to join his research group, and I guess I am very happy that I did as well. So the first of these talks was on the helium-3, helium-4 dilution refrigerator. I don't know how many of you people know how it works, but basically you have a mixture of liquid helium-3 and helium-4. The helium-4 is shown here in red. Helium-3 is in whatever this kind of blue-green is. And if you cool the mixture down, ultimately you get phase separation. So you have essentially pure helium-3 on the top, because helium-3 is lighter than, less dense than helium-4. And then down here you have superfluid helium-4. And the helium-3 atoms can propagate rather long distances through superfluid helium-4. So that you connect this now, this is called the mixing chamber, with what we call the still. Basically, you pump on the still. This is vapor and this is liquid, so it's a liquid-vapor interface here. And because helium-3 is lighter, in fact, the atoms vibrate more, the density is lower. Helium-3 tends to evaporate rather than the helium-4. And that causes more helium-3 to diffuse across this phase boundary. So that the helium atoms, basically in this bottom portion, the density is roughly a factor of 20 less than the helium-3 in this top phase here. And every time an atom propagated across that boundary, it enjoyed a larger volume, which meant, in fact, it had a higher entropy. So, in fact, that extra entropy came by absorbing heat from the outside. And that, in fact, is a device which virtually, I've seen several helium-3, helium-4 dilution refrigerators here just today. So this is a helium-3, helium-4 dilution refrigerator that I built as a graduate student during my first year of graduate study. I didn't do someone else built the gas handling system, the room temperature part of it. This is the mixing chamber, and these are heat exchangers which basically cool the helium-3 that's going down to the mixing chamber with the dilute helium-3 that's rising up. Those helium-3 atoms have a higher heat capacity, and so they quite easily can cool the returning helium-3. Now, the bottom of this has nothing to do with the dilution refrigerator. This is, in fact, part of this Pomeranchuk cell that Isaac Pomeranchuk had suggested. And here's the physics behind this, and it really seems quite remarkable, even though I've been faced with this almost every day of my life. If you look at the liquid helium-3 at low temperatures, it's a degenerate Fermi fluid. The entropy drops linearly with temperature, so that's what you expect. Whereas in the solid, the atoms are stuck at lattice sites, and there is, of course, a little bit of vibration, but we're going to be going down to very low temperatures, temperatures well below a half a degree Kelvin. And so then if you look at the solid, in fact, it has quite a large entropy, and that's because on each site you have an atom, and the nuclear spin at that site can either point up or point down. That's 2 states available per particle, so this is R log 2. And at some very low temperature, in fact, nuclear spin ordering occurs in solid helium-3. But below the temperature where these two curves cross, the liquid is more highly ordered than the solid. It's kind of an unusual situation in nature. I apologize. I realize that I'm pointing at this screen, and for you guys all over there, it's very difficult for me to point at both screens. I'm sorry about that. I won't try that. No, please come back. Oh, God. Let's see if we can find it now. I think it's Madrid is 3. It should be 4. This is, what a mess. 3. I don't know. I'm not sure if, I think it's supposed to have 4 pluses. Oh, wait a minute. Here we go. Okay. Yeah, here it is. Okay, good. Whew. Wow. Okay, so now, okay, so this is actually the parts of my Pomeranchuk cell. I didn't do much of the machining, but I loved freshly machined parts. And so this is the metal, we've gone, so this is where I was. Okay, so people tried to figure out how they would do this, and so people would have a very thin-walled tube which contained helium-3 inside, and then they this has helium-4 inside, and then as they increase the pressure, the walls would bow outward, decreasing the volume that was occupied by the helium-3, so the helium-3 pressure would rise. There are other types of these devices, and let me say that these are all, I don't think any of these things worked. So I decided to design my own Pomeranchuk cell. And what I did basically was had this here's the mixing chamber, which was, you've already seen that attached. You've seen this bellows on it. It's a large bellows. And you fill this with superfluid helium-4. It has essentially no heat capacity, no viscosity. It's wonderful hydraulic fluid. And that causes a force, which in fact pushes a smaller bellows into this helium-3 filled region. And now the melting pressure for helium-3 is about 34 atmospheres. Melting pressure for helium-4 is only 25 atmospheres. The reason this works, of course, is because the cross-section of this bellows is larger than the cross-section of the bellows down at the bottom. And so this basically is my Pomeranchuk cell, and down below we use a capacitive pressure transducer, which I think it dissipated less than a billionth of a watt into my Pomeranchuk cell, so it was actually a really nice addition to the apparatus. This, as I said, are some of the parts. This is the bellows that went inside the helium-3 filled region, which is here. This is the pressure transducer, and this is just basically to hold everything together. Now, right in the middle of that, I didn't tell you, I'd met a very pretty young Chinese girl almost the day that the two of us showed up for Cornell for graduate study. And so we dated for a while, and then the term started, and so I would call her up and say, Liu Xiaodai, how about a movie? I knew she liked movies. She said, too busy, hung up. This went on for, I don't know, a month or something like that, and eventually I gave up. But of course, the point is we got married, so something happened had to happen. Anyway, so we actually got married on August 14th, 1970. So this is Liu Xiaodai, Phyllis, AKA Phyllis, Liu Osheroff, and this is me, and gee, my beard was dark back in those days. We got married. Now, that's actually kind of interesting because as a graduate student, I apprenticed under another graduate student who was also married, but in fact, his wife had 2 kids, and she did not like the idea of living in what was called fertility flats. That's where married student housing was. And so essentially, I think he probably should have done the experiment that I did, but in fact, his wife wanted him to be home taking care of the kids. And I think he knows very well the sacrifice he made. Ironically, the marriage didn't last. Anyway, so then I had this Pomeraniec cell. What do you do with it? Well, there was another student named Linton Corricini who wanted to look at spin diffusion in helium-3 at low temperatures and low pressures, because in fact the spin diffusion did spectacular things then. And so he made most of this stuff. It's basically a wire heat exchanger which allowed him, me or whatever, to cool his helium-3 sample using my Pomeraniec cell. And so these are the data that you got. This is for different magnetic fields. There was a theory that would have been developed by Tony Leggett, who's a very famous person that perhaps some of you heard of. Anyway, he did not share the Nobel Prize with me, but in fact he did get the Nobel Prize for his work on superfluid helium-3 physics. So anyway, so you can't tell which one of these colored dots, red, green, or blue, should correspond to these 3 curves, which are for different magnetic fields. And so then we used that apparatus to get much colder, and in fact you can see very spectacular deviations from a straight line occurred. And in fact this is one of the things, this is called the effect of Leggett and Rice, and it was my first recognition that there was this guy in England who at that time, he wasn't a professor, he was a reader, was in fact a very smart person, and I needed. So from then on, I sent him all of my preprints. Anyway, so there was another group in the low temperature group at Cornell that had looked at, this was actually, so if you apply a large magnetic field, the melting pressure drops a little bit. But there had been a group at the University of California at San Diego that had used bad thermometry to look at that drop. And this was data by this very famous professor named John Wheatley. In fact, he was the one that founded SHE Corporation, which originally sold most of the helium-3, helium-4 dilution refrigerators that were made commercially before Oxford Instruments got into the business. So my thesis advisor, David Lee, suggested I redo this measurement, and here are my data, these red triangles, and they seem to be in rather good agreement, but there was a lot of scatter in the data. So I kept trying to get better thermometry, and eventually there were 2 other students that were waiting to use the labs. We didn't use superconducting magnets back in those days. It was an iron core electromagnet that probably weighed 10 tons or something like that. And so I had been using this thing, and so eventually these other students went to David Lee, my thesis advisor, and argued that I should have to give up this magnet. And David Lee agreed, and for that he shared the Nobel Prize, because if I hadn't given up the magnet, I would not have done the experiment that actually led to the discovery of superfluidity in helium-3. So I was very distraught because I needed the magnet for my thermometer. We were doing NMR thermometry on thin platinum wires. But I realized that I'd actually measured the melting pressure as a function of temperature. So I could use the melting pressure itself as a temperature. And so a few days after this event where I lost this magnet, I just decided I would compressed the helium-3 at a very constant rate, so the pressure rose. It rose because I was converting liquid to solid and the system was cooling. Melting pressure is higher at low temperatures. Here, this is on a strip chart recorder. Probably people here are not acquainted with that mechanism for keeping data, but anyone that has a white beard like this certainly remembers those days. So the pressure's rising. I rebalance the pressure. It's a capacitive pressure transducer, and it continues to rise. And then all of a sudden, at this point that I later labeled as A, there was a very sharp decrease in the rate of cooling, and I thought something surely had gone wrong. And so this was the day before Thanksgiving. I don't know if Spain celebrates Thanksgiving, but this was the day before Thanksgiving. And I realized, in fact, that I had the Thursday, Friday, Saturday, and Sunday to pre-cool my apparatus and start all over again at a lower temperature, because I'd started at 22 milledegrees, and for every millikelvin you cool, you convert something on the order of a few percent of the liquid into solid helium. And I assumed, in fact, that this was because the solid was being pushed on by the metal bellows, and so things were going very badly. So I tried to do this again the day after the Thanksgiving weekend. So this is the next Monday, November 29th, and so I'm going, cool, cool, cool. I'm going faster because I was a bit impatient. Rebalance the bridge and cool, and there it was again, this sharp decrease in the rate of cooling. And then I went back and looked at the pressure where this had occurred the first time and the second time, and it turns out that this was a very highly reproducible phase transition, totally unexpected in this mixture of liquid and solid helium-3. So I let this thing continue cooling, and then at a much lower temperature, I saw a little tiny drop in pressure, very instantaneous. It was clearly a first-order phase transition. And so ultimately, I had not discovered one, but two unexpected phase transitions in this mixture of liquid and solid helium-3. The question was, were these transitions in the liquid or in the solid? So, well, here's the first time, November 29th. This is about 6 p.m. I'm not sure when I went to dinner, and I said the rate of change of helium-3 pressure changed abruptly at this capacitance bridge reading, which had occurred in the last compression 2 at a point which was essentially identical. And I knew that this was no random event. This was a signature of some highly reproducible phase transition inside this mixture of liquid and solid helium-3. So eventually I found that I could see the A and the B transition was this little drop, both on cooling and warming. These were clearly real transitions. The question is, were these transitions in the liquid or in the solid? So Bob Richardson, who I shared the Nobel Prize with me, in fact, wrote all of this in my lab book. I actually don't have my lab book anymore. Let me tell you that if you get a Nobel Prize and then the Nobel people will come and they ask if you will give them your lab book, say no. So they have my lab book somewhere, but I don't have access to it. They actually gave me Xerox copies of all the pages. I have no idea where they went. Anyway, this is Bob Richardson's drawing all this stuff, and what he's trying to do is convince me that these transitions are in solid helium-3. And so, well, I don't know. I was a young, impressionable graduate student, and Bob Richardson was a very bright experimental professor, and so we published this thing, Evidence for a New Phase of Solid Helium-3. Now, I should tell you that this went right through the reviewing process with no questions or anything like that. And of course, the data was correct, but the interpretation was 100% wrong. So luckily, we got to try it again. Anyway, so we looked at this behavior. So rather than looking at the melting pressure, I decided to look at the solid NMR peaks. So, and I'll show you what they looked like. Oh, no, you don't get to see that. these are what the actual NMR data look like, and these are the peaks we're talking about. So, for instance, so here's what's happening is time is increasing to the left, because really I've turned everything upside down. These are troughs, not peaks. They're absorption troughs. So here we're coming along, and then all of a sudden it drops by a little bit, and then it continues. And this, I'm looking at this specific peak in solid helium. So let me go back to where we were now. No, okay. No. Am I going the right direction? Why am I not going? Where was I before? I'm going the wrong direction. Why is it? Well, let's go up. Is this where I was?
Yeah.
This is where I was. Okay, so actually, now I'm getting completely confused. I don't know why this thing's going. Okay, so now I'm looking for data. Here's the data. So you can see that the solid peak has a small offset on it, and that was exactly coincident with this drop in pressure. So I wrote in my lab book, if I can get this right, 2:40 in the morning. Now, this is a very good time to be taking data. There's less vibrations in the building at 2:40 in the morning. People don't bother you. There's less electromagnetic interference. I hope I've convinced all of you to work all night and then sleep from let's say if you can go. I'll allow you to go home at 4 a.m. Okay, so you sleep from 4 to maybe 8, and then you go back to work. That's the way it should go. So anyway, I decided to make a self-portrait of myself leaning against this iron core electromagnet. It was kind of interesting because, in fact, I only did the experiment that allowed me to discover superfluidity in helium-3 when these other two students took this thing away from me. So, in fact, absence was for me a very good thing. That is, absence of this magnet. So then I decided I would do some NMR experiments. I warmed the apparatus up and put in some NMR coils and things like that, and use that magnet. It was a high quality NMR magnet. And so this little red signal, let me show, all of these look about the same. This was in fact what the all liquid NMR signal looked like. But after I had grown a lot of solid, the solid has a much larger NMR signal. This is all solid helium-3. And so I think it was Bob Richards that suggested that we look at what happens using NMR. Eventually I got that magnet back is the point, and use NMR to see whether the transition is in the liquid or the solid. So this was all solid, presumably, and buried inside here was a little bit of liquid helium-3. And so we started cooling through that region where we saw the kink in the curve. And what we found was, in fact, that the liquid NMR frequency increased, and it moved to higher and higher frequency as we cooled further and further. I mean, this idea that you have an NMR frequency that is temperature dependent is absolutely ridiculous. But in fact, this was what Tony Leggett got the Nobel Prize for, explaining this. So I basically did measurements on several different magnetic fields. These are magnetic fields expressed as Larmor frequencies. And what I found was the data over basically a factor of 20 difference in magnetic field if you plotted the liquid frequency squared minus the solid frequency squared, or the Larmor frequency squared. Those data collapsed on a single line. So I sent this plot to Tony Leggett, and Tony Leggett almost immediately recognized what this is all about. So Tony figured that if you have helium-3 atoms that have formed Cooper pairs, that the orbital angular momentum now is pointing to the right. This is the L vector is what we call it, and the projection along this vector called D, which is related to these two spins, would be parallel to L. That's the lowest free energies condition, And then if you start doing an NMR experiment, let's see if we can see that, what happens is that we've tipped the magnetization. Boy, I'm sorry, I'm really sorry here. We've tipped, that doesn't work. I'm going to have to go back over it. But there are more people on that side of the room. Okay, so we've tipped the magnetization and it's processing about the magnetic field, and that causes this D vector to oscillate back and forth in the, now I can't even see what it is, in the Y-Z plane. But the equilibrium position, a position of lowest free energy for the D vector, is for it to be parallel to the L vector. So in fact, when you tip this thing away, in fact, it's causing an additional torque which causes the magnetization to oscillate at a higher frequency. And then Tony said, what happens, according to his equations, if one can apply an oscillating magnetic field not perpendicular to the static field, but in fact one which this is one which causes the magnetization to precess about the static magnetic field, and that causes the D vector to do this. And now, if you apply an oscillating magnetic field which is parallel to the static field, Leggett's equation suggested that the D vector would oscillate in the XY plane. And all of that ended up being the case. And so here was basically, I basically, this is the data that showed that Tony Leggett's results were correct. And so, but Tony had also suggested there are two phases. There's an A phase and a B phase. And in fact, Leggett suggested that the NMR frequency shifts in those two phases should be related to one another. And so here's the data. This line is the Larmor frequency in the A phase times the square root of the ratio of the susceptibilities to the 1/2, well, to the square root. And these other triangles are in fact measured values of the Larmor longitudinal resonant frequency in the B phase. So what this means is we are, if I go back, so we're actually applying an oscillating field parallel to the static magnetic field, and that causes the D vector to oscillate in that plane. So here we are. Okay, so that's that. And so at this point, I would think we knew quite well what these two phases are. Now this is helium-3 phase diagram in 3 dimensions. This is pressure going upward, temperature to the right, and magnetic field into the board. So this top plane here is the melting plane. This is the plane along which liquid and solid helium-3 coexist. And this is the A superfluid, and this, the yellow phase is the B superfluid phase. But in addition, there were ordered phases of solid helium-3. What an incredibly rich phase diagram for something as simple as helium-3. So in fact, I decided ultimately, this is after I finished with the work which identified these two superfluid phases. I looked at the solid phases, and this is some prediction that had been made by let's see, it's Daniel Fisher and Mike Cross, two of my favorite. I love working with theorists because they know all the answers that I don't know, but I'm the one that controls the cryostat. So in fact, so there were actually, for a single crystal of solid helium-3 at below the temperature where the nuclear spin's ordered, you should see 6 different NMR lines, 1, 2, 3, 4, 5. This one was too low a frequency for me to actually make some measurements. And so the question is what you call this thing. Now the theorists always get to name things. And so they call this the UUDD structure because you have planes of spins. So this is one plane, and you have 2 planes up, this plane and the next plane, which passes through the body-centered cubic atom. This is the second plane. So you have up, up, and then down, down. So they called this the UUDD phase. But then the Empire Strikes Back, the Star Wars sequel, came out, and I was reminded of the fearless robot warrior R2-D2. So I named this phase U2-D2 after R2-D2. And I hope he loves that, even though he's not a real person. And my wife was kind enough for my birthday to give me a license plate, HE3U2D2. And I can tell you, I think no one looks at that license plate and realizes that it is a vanity license plate. But stand up, Phyllis, stand up. This is my wife. Anyway, so it's I've been driving that car for a long time. It needs a new license plate. So here is David Lee, my thesis advisor, and Bob Richardson, and me, and we're showing off our new Nobel medals. Now, it's kind of interesting. I can't remember when gold hit, I think $1,500 an ounce. I took the Nobel medal out of the safe deposit box, and I said, how much does this damn thing weigh? And it was pretty heavy. And so I said, well, you know, is it pure gold? And so then I Googled Nobel Prize medal. And what you find is it's I think it's 20% silver and 80% gold. And so then I said, is it worth selling this thing? God, 'cause gold is $1,500 an ounce, and this thing weighs a lot. The bottom line is I still have the medal, and of course it's still in the safe deposit box where it does me no good whatsoever. Anyway, so and then I dare say you can't give more than 3 people a Nobel Prize to 3 people for the same piece of work. So Tony Leggett, who did the theory of everything else, everything that I did later. So let's go back here. This is Ashraf, Richardson, and Lee in, well, I can't remember, 1996. And in 2003, Tony Leggett got his own Nobel Prize, which he shared with 2 Russians. It's sort of interesting. In physics, I think almost most of the time, Nobel Prizes are shared. So the physicists end up getting less money. But I can tell you, the Nobel Prize is not about money. It's about fame and glory. So here's a picture of my apparatus again, and now what I've done is I have put the names of people that contributed knowledge or ideas that were necessary for me to make this discovery. So Pomeranchuk, who suggested the refrigeration technique that I used, Anuferev, who was the first one that actually did that kind of cooling, and then Bardeen, Cooper, and Schrieffer, of course, for their theory of superconductivity, which remarkably is applicable to superfluid helium-3, even though there's no lattice. That's a bit complicated, but it's understood. Phil Anderson, who ported the BCS theory to helium-3, Tony Leggett for understanding the spin dynamics, which really allowed us to understand the nature of these ordered phases, and then Ed Hamel for his work for not throwing away the helium-3 into the atmosphere because it was slightly radioactive. And then John Wheatley really did a lot of the development work for helium-3, helium-4 dilution refrigerators. Lev Landau, of course, for his Fermi liquid theory. Strady and Adams, anyway, the bottom, we're not done. Edwards and Hall invented the helium-3, helium-4 dilution refrigerator. Bloch and Purcell invented NMR. You know, I would say without any one of these collection of names, I wouldn't have made the discovery that I did. So let me just close by saying that advances in science are seldom made by individuals alone. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. And this is how advances in science are made. Thank you very much. Now, I hope that the graduate students in the audience will go back to their labs and maybe a little bit more excited about their research. How do we do? A question and answer session.
Yes, so maybe before going to the lab, the younger students can ask some questions, and of course also the not so young.
Okay. Yeah, I don't guarantee that I know all the answers, but I'll try. No one has any questions. Oh, this is a forlorn group.
Everything understood?
Oh, come on, you guys. Well, okay.
Maybe I can't.
You ask me a question. Okay.
So actually, you said that you took solid helium-3, right? Oh, there is a question there.
Oh, okay. Okay. Go for it.
Very good.
I wanted to ask what kind of heat exchangers you have in your original
dilution refrigerator. Yeah, that's kind of an interesting question. They were basically, it was copper felt. We punched these things out and stuffed them in a hole under pressure. And so it didn't have a very large surface area, but it was still able, I was able to get down to 15 milledegrees. Didn't have much cooling capacity at 15 milledegrees. Okay, that's a real nuts and bolts question. Have you made one, a dilution refrigerator yet? Okay, not so hard to do.
More questions?
Yes?
Yeah. Would you advise a young physicist to start doing experimental work with helium-3 nowadays?
Of course not. I think it's really pretty well understood now. I mean, I would love to be proven wrong, okay, but there have been people studying helium-3 for probably 30 years, superfluid helium-3 for 30 years all over the world, and it's sort of, I think it would be really sort of surprising if that all of those people missed something, but you know, you never know. So, but there's so much else to study. Yes.
So what is the future of supply of helium-3? Because I heard that there are big problems now. There is no Cold War.
Yeah.
That's where we start. And I think that we have a big problem with the supply of helium-3.
Yeah, well, it's sort of interesting. It turns out that in the United States, the real problem isn't with what you just said. It's that the Department of Homeland Security recognizes that helium-3 atoms have a huge neutron absorption cross-section. So, in fact, you can use helium-3 maybe under pressure as the world's most sensitive detector of free neutrons, and that's a serious problem, I think. But tritium decays with a half-life of 12.4 years into helium-3, and it may be that we're not building more hydrogen bombs, but I can assure you we are maintaining the ones we have, and which means, in fact, that the Department of Energy, or whoever does that, is continuing to manufacture tritium.
But I think the price has increased roughly a few times in a couple of years.
Yeah, what is the price? What is the price now? I don't know.
I think it's around, yes. Well, you should know because of ILR, right?
2,500.
For per liter? I've got a lot. Okay, I'm skipping the country and I'll sell it on the black market. When all of the stuff I used, I think helium-3 was $300 a liter. Wow, that's a lot. So is it? I don't believe it is because we're not producing more helium-3, because we are, as long as we have a nuclear stockpile.
Is the consumption of the production?
Well, that's, yeah, I think it's also one of these things. As soon as the Department of Homeland Security threatened to take all of it, then people started gobbling up and saving as much. And I will say that I have a nice...
They make a rule now that they are really forbidden to use for this big detector, because the idea was to have this big detector on the entrance of all the highways and all the harbor of the United States in order to control the fission program.
Yeah, we don't have...
Now they really give up, and they have a new technology based mostly in volunteer.
Yeah, I mean, there's just not enough helium-3 to do with what they wanted to do. Okay, interesting. Any more questions? Yes?
You have not recommended more research maybe in helium, but in your opinion, what could be the most
interesting challenges or new research lines in the world of low temperature physics for in the near future? What's hot in your opinion?
Hot. I mean, you know, I don't know. People are looking at all sorts of interesting, mostly looking, I think, at solids at low temperatures now. I certainly, well, first of all, the only thing that is liquid at these temperatures is helium-3. But you know, I think there is a lot of solid-state physics that is probably best studied at low temperatures. Now, that doesn't, I mean, you can do that with a helium-3, helium-4 dilution refrigerator, and I think there are several such dilution refrigerators here. The huge ones that Oxford Instruments sells, those things, probably each one of them has a mole of helium-3 in it, I think. And I think that when the Homeland Security said that they were going to claim all the new production of helium-3, I think that caused a run on the market, and people started buying helium-3 as insurance that they could use it later on. So I don't know, but you know, obviously there's a lot of condensed matter physics that can best be done at low temperatures, and I think that will probably require people to have helium-3, helium-4 dilution refrigerators. I mean, the fact that as a first-year graduate student, I could make a dilution refrigerator that went down to 15 thousandths of a degree, trivial technology, right? Okay. Yes? Wait a minute. What questions can you possibly have that I haven't answered already?
The key is this dilution refrigerator invention in '65, right?
Yeah.
Helium-3 has a finite percent solution in helium-4. Did any theorists predict that?
I don't know, but I would guess not.
But I think too.
Yeah. You think you can Google that? It is remarkable what you can learn from Googling things, and of course it's so funny that Google has become a verb. Yeah.
Okay, so
Yeah.
Alfredo.
What do you think about these proposals to generate Majorana fermions based on helium-3? I think theoreticians at Stanford have proposed that.
Oh, which ones?
Zhang.
Xiaocheng?
Yeah.
Oh my goodness. Well, he's not trying to get me to. He knows that I'm retired, so. No, but there. Yeah, I'll have to. Oh, thank you. I'll have to talk to Xiaocheng about that. Yeah.
He can acknowledge you in the paper.
What? Well, you didn't make me a co-author, that's for sure. Okay.
Okay.
Well, thank you all for coming, and I hope you enjoyed this. I dare say, you know, physical research, experimental research is just, for me, it's been a lifetime of love and caring, and I'm envious of all of you people that are still doing research, and I'm retired. But the reason I've retired is because I spend so much of my time going around the world giving talks like this. Thank you for coming.